Bismillahirrahmanirrahim. Assalamu alaikum. My name is Jim Shedri and my role ID is 190994. So today I'm going to discuss the some task performing in C language. First of all, we have to perform on our ATMEGA studio, AVR studio, and then we have to implement it on Proteus, and after it we have to implement it on hardware as well. First of all, we are using here two softwares, AVR Studio and Proteus. So for comments bar, we are using these bars for commenting in our ATMEGA studio. So first of all, we have to create a executable C project, and then after it we have to include all the files, such as for delay we have to include AVR delay respective with including header respective functions. So these are some operators such as DDRB, X0XFF, or the +4 operator for adding 1 as in counter. So this is the main function. So when we are declaring our function, we have to declare all the function in our main function. So this is the flow control statements that indicate the order in which a series of actions are performed. So for example, here our function starts from 1 and goes to 128, and then after it multiply with 2 and do something again, our function run. So this is our function. This is a basic introduction toward this function, and this is our delay loop function, and then it will cause delay in our program. So encapsulation of the code in which keys is a key idea in C programming and helps make chunks of the code more convenient to use. And just as important, it provides a way to make tested code reusable without having to rewrite. So encapsulation is mainly used for using code again and again when we are performing on our some Proteus or simulation as well. So why we are using program in C? Because it is easier and less time consuming to write in C than in assembly, because assembly program is too large, and C is easier to modify and update. Also we can use code available in function libraries. So most of the functions are available in our function libraries, so which we are including on the top. So C code is portable to other microcontrollers with little or no modification. So these are the data types used by C compilers, such as unsigned character of 8-bit 0 to 255 maximum, character 8-bit -128 towards 128 positive, unsigned 0 to 65535, 16-bit int 16-bit -32 768 to 32 767, and unsigned long 32-bit from 0 to 4294 967 295, and as long as long from negative to positive half, and then float from plus minus 1.7 exponent 5 exponent -38 to positive -3.40238, as well as double of 32-bit from positive to negative value, as same as float. So this is our first example. We have to write an AVRC program to send values, maximum values 0x0xFF to port B. So first of all, we have to include standard AVR header, and then in the main function, and then in the main function we have to initialize unsigned character Z, and with the help of direction register we are setting port B as output. So this is our for loop, which begins from 0 to 255 on the port B, and after it our function will return. So if we are move toward its code on ATMEGA, so you can see here, first of all we declare function Z and its output as port B, and then this Z function start from 0 to 255 on the port B, and then function return. So you can see here the maximum value is shown here from 0 to 255, means 0xFF to the port B. So now we are going towards our second task, which is AVR program to send hex values from ASCII characters. So this is the hardware implementation of 0xFF to the port P output. So now we are going to perform an AVR C program for sending hex values of ASCII characters and to the port B. So first of all, we have to include standard AVR, then main function and unsigned character my list. This is array. So this array includes all the ASCII characters 0 to D. So we have to declare here unsigned character Z, and then with the help of direction register we have set the port B as output, and then after it we apply a for loop from 0 to 9, means 10 times. So after each increment it repeats 10 times. So port B declare and send the character, then this loop send the character to the port B one by one, and then after it our function will return. So all the ASCII characters tend to the port B. So if we move towards its simulation on ATMEGA Studio, so this is our code. So here we use some delay. So after some delay, next character shown on port B. So if we are not creating delay, then our function direct set 0 to D. Then it runs so fast that 1 2 3 4 5 ABC doesn't show. So that's why we are using here some delay. So this is our delay include file. So this is our delay function. So with the help of this delay function we can easily appear 0 1 2 in a sequence. So as you can see here, DD, the ASCII values of D character, which is the last character, is 44. So this is shown on our Proteus simulation. So after uploading hex files on Proteus of this ATMEGA Studio build solution, then we can easily run our circuit, and our D, which means 44 value, is shown here. After it our function will stop because this is our last ASCII character value. So now we are going to move our third task. So this is hardware implementation. As you can see here, 41, which means the A, B, C and D, means A value is shown to the hardware when we are performing on hardware in our lab. So now we are going to move our third example, which we have to write AVRC program to toggle all the bits of port B 200 times. So for toggling, first of all we have to declare standard AVR header and then main function, and then we have to set the port B as output and port B as output, and then we have to send the port B 0xA, mean 101010 values, and then unsigned character G, and then with the help of a for loop this function will run 200 times. So port B, here this statement includes that port B is equal to not of port B, means this function will toggle the value at each loop. First it will appear 101010, and then it will appear in next loop 010101. So after it our function will stop. So now we are moving towards our ATMEGA simulation. This is our code. So here we delay call delay function for proper appearance of our all the toggling inputs. So now you can see here when we are performing on our Proteus, when we perform here and upload export our hex file of our build solution, then our LEDs start blinking 0101010101101010. So in this way our LEDs continuously blinking one by one, means 010101. So this is toggling in this way. So this is the hardware implementation on our AVR microcontroller ATMEGA 328P in our lab. So now we are going to move towards our fourth example, which we have to write an AVR C program to get a byte of data from port B and then send it to the port C. So first of all, we have to declare the standard AVR header and inside character, which is the temporary character, and then set the port B as input and port C as output. So such as we are giving some input to the port B and it will store to the temporary value, and this temporary value is sent to the port C, which is as the output port. So this is the code. Here we call some delay for displaying proper appearance on our Proteus or somewhere in lab or hardware as well. So now you can see here, if I am giving 0 1 0 0 0 0 1 0, then it will appear 0 1 0 0 1 0 1 1 1 0. So now you can see here I am sending data from the port C, and then I am getting data from the port B. So in this way our Proteus simulation works. So I'm sending to the data to the port C and then getting data from the port B. So now this is our hardware implementation of this task. Now we are going to move towards our a fifth example, which is just like about the operators we are using here. Now you can see here this DDRB 0xFF register used to set port as output, and then these three port is set to the output port B C D with the help of 0xFF, and then this operator used for ANDing operation, this is ORing operation, this is XORing, and this is inverting operation. So now we are going to move towards our sixth operation, which is write an AVR-C program to monitor bit 5 of port C. If it is high, send 55H to the port B, and otherwise send double AH to the port B. So first of all, we have to define standard AVR header and then set the port B as output and port C as input. So after setting port B as output and port B is input, we are here using while loop. If pin C is 001 00000, and then it will check the bit 5, mean fifth bit means sixth bit of pin C, means 5 number bit consisting of 6 bit, means starting from 0. So then it will send to the 0x55 to the port B, and otherwise it will send to the, if it is not equal to then 001 000, then it will send to the port B 0xAA. After it our function will return to 0. So this is the ATMEGA Studio simulation of our code. Now after getting hex file, we are going to upload it on our Proteus circuit. So when we are uploading it on our Proteus circuit, as we can see here, I'm giving value to the 0 0 0 0 0 1 0 0, mean this is the value which is equal to 001 0000, then it will send 0x55 to the port C. So here you can see this value is sent to the 0x55 is sent to the port C. So port C displaying us 101010. This is the 0x55 value. So when I'm just hearing just like giving 0 to this bit, then it will shows 0xAA mean 010001 in reverse of it. So this is our basic Proteus simulation of this task. So now this is performing on our hardware as well. So now we are going to move towards our lab activity. You can see here we have to write a code that takes input from port B and checks whether the number is even or odd. If the number is even, then we have to blink LED of port C with a delay. If the number is odd, then we have to blink LED of port C one after another from LSB to MSB. So first of all, we here declare our code such as we have to set the frequency and then include AVR header, and then include delay function, and after it we have initialized our main function with the help of 0x00. We set as a port C as a input, and then send the 1 maximum value to the port D and set as an output. So with the help of while loop, if pin C is 00000001, then our port D is this value, and after some delay our port D is 100, and after some delay our port D is 00100, and after some delay our port D is 01000. So in this way it will changing its values on the port D with some proper delay. So as you can see here, it will gain sending one by one value to the port B, 0001 So in this respective way it will send all the values to the port D with some proper delay. So now if we are going to implement it on Proteus, so as you can see here I am giving some function such as 0 0 0 1 0 0 1 0. So now then in this case our function will call 0 1 0 1 0 1 and 0 1. Otherwise our function will call random values if the pin is not equal to 0 0 0 0 0 1. So this is our Proteus simulation of our function. If the function is even, then it will shows 0 1 0 1 0 1 0 1, and then if it is odd, then it will blink LED one after another, means first 0, then after this one, and then after this one, and after this one, and then one by one. So if it is even, then it will shows 0101 in your case. So now you can see here function is here that 8-bit number. When we are converting 8-bit number to the decimal, then we can see this is even number. So then even number, it means it shows 010101 and 01. So now we are going to move toward its hardware implementation. So this is our hardware implementation. We are implementing it on our hardware. So as now you can see here, I am giving the even value or odd value, so it will blinking one by one. So in this lab we learn how to show output on different parts of microcontrollers, and with the help of C program language we perform different tasks on the microcontroller, such as these LED blinking in case of even or odd or etc. So that's all from my side. Jazakallah.
ये हमारी हार्डवेयर इम्प्लीमेंटेशन है काउंटर की, तो जिसमें हमने आर्डिनो के ज़रिए 7 सेगमेंट के ऊपर काउंटर डिस्प्ले करवाना था 0 से 99 तक। सो ये हमारा हार्डवेयर पे इम्प्लीमेंटेशन है काउंटर्स की, जो कि 0 से 99 तक वैल्यूज़ डिस्प्ले करवाएगा।